The question that I have is, could you do an example on frictional problems involving rotational relative motions? In the theory video, we have considered these problems and derived an expression for the torque needed to produce a rotational motion on the contact surface, overcoming the friction, right? In the first case, we have a pivot bearing over here and a flow sander over here, both of which have the same expression for the torque, M, right? So M is given by this expression right here, M equals 2/3 times mu times P times R, where mu is the coefficient of friction of the contact surface, P is the total applied normal force, R is the radius of the circle. So here we have the collar bearing, where the contact surface is annular with an inner radius R1 and an outer radius R2. This is the expression for the torque. Here we have a brake system involving brake pads and a rotor. Here the geometry of the brake pad is approximated into a segment of an annular area with an inner radius R1, outer radius R2, and an angle of alpha. This is the expression if there is a pad on one side of the rotor, and this is the expression if we have pads on two sides of the rotor. The torque for double pad is simply twice the torque for a single pad. Let's see if we can do some simple examples to illustrate the use of these equations. This is our first example. This involves a flow sander. The radius of the flow sander is 0.5 meters and the weight of the sander is 100 Newton. The coefficient of kinetic friction of the contact surface is 0.5. The sander spins at a constant angular velocity. Determine the torque that the motor must exert to keep the sander spinning. Assume that the contact pressure is uniformly distributed. We'll make use of the equation we saw in the earlier slide. This is a fairly straightforward problem. The sander is spinning at a constant velocity, so we should employ the kinetic friction, right? So the coefficient of kinetic friction is given as 0.5. The radius of the sander is 0.5 meters, so it has a full circular contact surface. The weight is 100 Newton. The weight of the sander serves as the normal force on the contact surface, and we can assume that the contact pressure is uniformly distributed, right? And therefore this equation is valid, and here are the numbers for the parameters in this equation. Substituting these numbers in this equation, we get a value of 16.7 Newton meter for the torque. So this is the torque that needs to be exerted by the motor in order to keep the sander spinning at a constant angular velocity. Here's our second example, and this involves a double collar bearing. The axial force on the bearing is 100 kilonewton, and this axial force is going to be acting collectively on collars 1 and 2. It's given that 70% of the axial force acts on collar number 1, which is the bottom collar, and the remaining 30% acts on collar number 2, which is the top collar here. The coefficients of frictions are given, and the necessary inner and the outer radius of the annular region for each of the two collars are also given. The question is to determine the value of the minimum torque needed to initiate a rotational motion. So this will be the torque that is needed to overcome the frictional forces on the contact surfaces. Once again, we'll make use of the equation we saw earlier for a collar bearing. This is the minimum torque that is needed to overcome the frictional force on a single collar bearing. So we just have to find the resisting torques on each of the two collars separately, sum them up to find the total torque. Here I listed the values for the parameters that are relevant to collar number 1, and then using this equation I get a torque of 653.3 Newton meter. Here are the corresponding calculations for collar number 2. Summing up the two, the total is 805.3 Newton meter. So this is the minimum torque that is needed to initiate a rotational motion on this double collar system. Here's our example number 3, which involves brakes. The geometry of the pads here, the brake pads, can be approximated into a segment of an annular area with an inner radius R1, outer radius R2, and angle alpha. The values for these parameters are given over here. The normal force that is applied in order to apply the brake is 1.5 kilonewton. The pads are used on both sides, two sides. The coefficient of friction between the pad and the rotor is 0.4. The question is to determine the stopping torques exerted by the braking pads. We will go ahead and make use of the equation we have derived in the theory video. So I listed the parameters here, and using these parameters in this equation, the torque for a single pad is 10.6 Newton meter. The torque for double pad, that is pads on both sides of the rotor, is 2 times that. So I get 21.2 Newton meter for that. So this is the total stopping torque for this system. If you are wondering what happened to the angle alpha, well, it doesn't show up in this equation.